Welcome to ARA Solutions channel. In today's video, I'll be presenting to us the resultant of two-dimensional concurrent forces, and I'm quickly going to give a brief explanation to two-dimensional systems. By two-dimensional system, we're talking about a force system that we can actually visualize on a plane. That is to say, we can use just two dimensions, maybe just an horizontal axis and the vertical axis, to describe the direction of each and all of the forces acting on the system. And when we have this kind of system, we say we are dealing with a two-dimensional system or a planar system. That's a system of forces acting on a plane. Then when we talk about concurrent forces, we're just looking at a set of forces that tend to meet at a point. Like this force, for example, we can quickly say that all of them meet at a particular point, which we would take as our origin in our Cartesian coordinate system. So we're quickly going to progress to see some examples that borders on resolving such forces to components and estimating resultants, as well as working out an unknown if the resultants of these forces are given. The first one we're quickly going to see is how to resolve a force into component for two-dimensional system. So if we have this particular problem and we have a man pulling a pipe with a string that is attached to the pipe, and we have the direction of the pulling, that's the direction of the tension with which the man pulls the pipe. And there's a question before us. Given that the man pulls the pipe using the attached string with a force of 500 Newton inclined at an angle of 60 degrees to the horizontal, find the vertical and horizontal components of the force. If we have a problem like this, that we move onwards to draw out what we call a free body diagram. By free body diagram, we mean a diagram that shows all forces acting on it with other bodies detached from it. Like for this case, we are seeing just the force, the 500 Newton force attached to the pipe. We have to take away the man and its string. And of course, there's a coordinate system. And of course, the direction of the force, which is 60 degrees to the horizontal axis. We can easily bring out what we call the free body diagram, showing just the force and its direction. Having produced the free body diagram, the question requires us to determine the components of the forces in the horizontal direction and in the vertical direction. It is important I point out that one can easily determine that by saying the component of force in the x direction, let's call it fx, is equal to the force itself, which in this case is 500 Newton, multiplied by cosine of the angle it is making with that axis. In this case, it is 60 degrees. And you can also do same for the y-axis. Fy, which is the component of the force in the vertical axis, is equivalent to the value of the force multiplied by cosine of 40. Now, this is one way to resolve to components. Alternatively, one can say that f of x is equal to 500 cosine of the angle it's making with that particular axis, while f of y is equal to 500 times sine of that same angles. F of s is equal to 500 times cos 60, and that will be 250 newtons. And likewise, Fy will be equal to 500 times sine 60, or 500 times cos 40, and that will be equal to 433.01 newtons. To resolve this force 500 newtons to the x-axis is going to be acting in the same direction as the x-axis. As a result, what we have here is positive. However, if we resolve this same force to the vertical axis, we are going to have the Fy component pointing in a direction that is opposite the Y direction. As we can see, our Y direction of the force is upwards, and this one is pointing downward. So what we have as our sense or direction of the Y component is negative. Let me quickly show how this cos and sine are taken for each of the components. Now let me quickly demonstrate how these formulations are derived. If you have our free body diagram as shown, you can quickly reproduce this diagram in form of a triangle, Fs pointing in this direction, and we take this as our Fy component, Fy pointing downwards, and we have our resultant, which is the 500, or should I say, and we have our magnitude of force, which is the 500. This place that closes this 500 is equivalent to Fy. Let's not forget that we have our angle, which is 60 degrees, and since our angle is 60 degrees, one can easily state from our basic trig ratios that the opposite side over the hypotenuse. For this case, the opposite is Fy. So Fy over hypotenuse, which is 500, which will be equal to sine 60. As thus, Fy is equal to sine 60. Likewise, Fs divide by the hypotenuse, we are likely going to get cos 60 degrees. And as thus, one can easily say that Fs is equal to 500 times 60 degrees. And that is how our formulation is obtained, such that Fs will be equal to 500 times cos 60 and Fy will be equal to 500 times sine 60, and Fs will be equal to 250 newtons and Fy will be equal to 433.01 newtons. Noting that because Fy is pointing downwards, because the component of the force when resolved in the y-axis is pointing downwards, y when resolved vertically is pointing same direction as the x-axis, we can say that this is negative and this is positive. These are the different components of the force, such that we can write our force to be equal to 250 I minus 433.01 J, and all this is in newtons. So we're quickly going to see another example that involves finding resultant of two concurrent forces. So if we have the same system, but this time around we have two people pulling the pipe from two different directions, and they have their respective directions as well. We can quickly see that these two forces meet at a point. So if there's a question before us, the question reads thus: the man pulls the pipe with a force of 500 Newton inclined at an angle of 60 degrees to the horizontal, while the lady pulls the pipe with a force of 400 Newtons inclined at an angle of 40 degrees to the vertical. Find the resultant of the two forces and its direction. We are quickly going to bring out our free body diagram. We have our coordinates x and y axis, and we have the force with which the man pulls the pipe to be 50 Newtons and at an angle of 60 degrees to the horizontal, while the force with which the woman pulls the pipe is 400 Newtons and at an angle of 40 degrees this time around to the vertical. So we can quickly bring out our free body diagram as shown, assuming the pipe is a particle, that's neglecting its dimensions. We are going to try to first solve it using the diagrammatic approach, wherein we are going to produce a parallelogram of forces. Then we will go on to produce a triangle of these same forces acting on the system. And in doing that, we need to draw what we call parallelogram of forces. According to the principle of parallelogram, if you use two sides of a parallelogram to represent two different forces, both in terms of their directions and their magnitude, and the diagonal drawn from the point of intersection of the two forces represents the resultant of the two forces. But before we draw the diagonal, it is important we first make it a closed parallelogram. So if we've closed this, we can therefore easily draw the resultant from point of intersection of the two forces, and that represents the resultant of the two forces. It is important we note that since this is parallel to this one, this dimension is also equal to 400 newtons, and we can quickly find the angle here that is unknown. Let's quickly produce this, and we're looking for this angle. To find that angle, we're told that this one makes 60 degrees with the horizontal, while this one makes 40 degrees with the vertical. So we can have that this is 60 and this is 40, 90, and this is 90 minus 40, which is 50. It therefore means that the whole of this angle is going to be 110 degrees. An alternative way that we can produce this diagram is to draw what you call a triangle of the forces. To draw a triangle of forces, you draw one force. Let's say this is our 500 Newton force. Since it's acting in the same direction as the 500 Newton, then you draw the second force from where the first force ends, and this is our 400 Newton force acting in the same direction as the 400 newtons. Then you close the triangle. To close the triangle, you have to start from where you started, and you draw a line to meet both of them. And if you do that, this angle is 110 degrees. Then one can quickly use the cosine law or in this case, the side that we are looking for is equivalent to our resultant. So r squared is equal to 500 square plus 400 square minus 2 times 500 times 400 times cos 110. So invariably one can work that out to get our resultant r to be equal to 739.46 newtons. Then we may want to determine the direction of the resultant as well. Of course, if we remember our triangle, and we have this to be 110 degrees, and we've gotten our resultant, and this is 500 and this is 400 newtons. To find the direction of the resultant, which is the angle it's making with any of the axes, one way to do that is just to find an angle that this particular resultant is making with this force, 500 Newton force. If you can get that angle, you can use trig relationship to determine the angle it's making with the horizontal. And to do that, you need your cosine formula. A over sine of the angle that is facing the side is equal to b over sine of the angle that is facing side b. And in this case, we have our resultant, so we can say resultant over sine of the angle facing the resultant, which is 110, is equal to 400 over sine of the angle facing 400. And of course, if you cross multiply, you can quickly discover that sine alpha is equal to 0.5085, and alpha will be equal to 30.55 degrees. That is to say, if we have our resultant is making an angle alpha which is 30.55 degrees with the 500 Newton force. We are aware that 500 Newton force is making an angle of 60 degrees with the horizontal axis. So one can say that R, the resultant, is making an angle of 60 plus 30.55 with the horizontal axis. So our resultant invariably is at an angle of 90.55 degrees with the horizontal axis. Let's quickly try to solve the same problem by resolving two components. We are going to progress by first looking for the components of the 500 Newton force. Let's not forget that 500 Newton force is making an angle of 60 degrees with the horizontal, and this will be equal to 500. If you want to resolve that to the horizontal axis, you have to multiply by cos 60 I. Well, I'm using I to indicate the horizontal axis. That's the unit vector in the horizontal axis. And if you are resolving that to the vertical axis, we are going to have times 500 plus 500 times sine 60j. We've looked at how to resolve forces to components earlier, and we must note that for this case is going to be negative because our 500 Newton force when resolved to the vertical axis is going to point downwards, which is away from the direction of the y-axis. So we're taking that as negative. If you do same for the 400 Newton force, we are likely going to get 400. Of course, we know that 400 is at an angle of 40 degrees this time around to the vertical. So this will be equal to 400 times sine 40 degrees I. And this time around is going to be negative because if you resolve this 400 newtons to the vertical axis, it's going to be pointing away from the x-axis. So we have minus 400 Newton, minus 400 times sine 40i, and of course we have 400 times cos 40j. This case is also negative because by the time you resolve the 400 Newton force vertically, it's going to be pointing downwards, which is in the opposite direction of the vertical axis or the y-axis. 500 newtons at an angle of 60 degrees to the vertical to be equal to 250i minus 433j. And likewise, the 40 Newton force, which is at an angle of 40 degrees to the vertical, will be equal to minus 257.11i minus 306.42j. So to get the resultant, we must recall that our resultant is equal to F1 plus F2. That is equal to 500 angle 60 perpendicular plus 400 angle 40 perpendicular. So we're going to quickly add the components of each forces. That's the component, the I component of this 500 Newton force and the I component of the 400 Newton force to get our resultant components in the x-axis, and that will give us 250 minus 257.11 will give us minus 7.11 I. Then of course if you had the y components of the different forces together, we are going to get minus 433 plus minus 306, and that will give us minus 739.42 J. This value we get here is our resultant. Although it is in its component form, we can quickly get those values in the magnitude of, we can quickly get the magnitude of the resultant by just using our simple equation that is used to determine magnitude, which becomes 7.11 square plus 739.40 square, and our answer becomes 739.45 Newton, and this is our resultant. To find the angle of the resultant, let's quickly note what we've obtained. We've determined quickly that this force has two components. One component is minus 7.11 I, and the second component is 739.45 J. So we must be able to represent same in our Cartesian coordinate system. Let's quickly recall that our resultants, the components are minus 7.11 I and minus 739.42 J. That is to say, because the resultant has negative component of x-axis, if this is x-axis, is going to be around this region, and it has negative components of y as well, so that is to say it's going to be around this region. So where does the two regions meet? It's going to be this plane. So our resultant is going to be on this plane. That is to say, if we are drawing our resultant, we are going to have something like this. So to bring this out properly and clearly, we're going to have this. This is our x-axis and this is our y-axis, and our resultant we know is going to fall out like this. If you have that, let's quickly recall that we already know some of these components. This is 7.11, which is our x component. This is 739.42, which is our y component. And of course, our resultant is 739.45. What we are looking for is this angle theta. And to find theta, you can use any of your three relationships. So let's quickly take cos. Cosine of an angle is equal to adjacent, which is this side, the side that's adjacent to the angle, with 739.42 divided by, this is 739.45. You're going to have cos theta is equal to 0.99995. And if you find the arc cos of that of 0.99995, you are going to get 0.55 approximately, which is what we had earlier. So one can say the resultant is equal to 739.45 at an angle of 0.55 degrees to the vertical axis acting downwards, or you can add up the 90 degrees between the two planes. Let's not forget this is 90 degrees, so you can add up that 90 degrees to the 0.55 and also say that resultant is 739.45 at an angle of 90.55 to the horizontal axis. So to summarize, we have looked at example of resolving forces into components. We've also seen different ways we can add forces via an example. This will be all for now. I sincerely do hope you found the video helpful. I want to thank you so much for spending time to see this video, and do well to subscribe to my channel to see more of such videos on engineering mechanics.